Hello everyone, this is the third video of our trigonometry short course series. Previously, we have discussed trigonometric functions and how to solve algebraic equations that contain these trigonometric functions, as well as some fundamental properties of these trigonometric functions and some very well known and frequently used identities of these trigonometric functions, including sinus, cosinus, tangent, and more. Here in this video, we will be discussing applications of trigonometry in electrical circuits and signals. Trigonometry has different uses in many subfields of engineering discipline, and especially in electrical engineering, we have very important usage of trigonometry, and the most fundamental and basic topics are electrical circuits and signal processing, etc. Of course, we also use trigonometry in more advanced topics, but in order to understand how trigonometry is used and how it affects our designs, analysis, and synthesis of electrical equipment and systems in general, it's a good starting point to analyze circuits. Today we will mostly focus on circuits, but we will add a flavor of signals as well. We will first look at signals and how they are coded, or let's say represented, using these trigonometric functions. And we will see their usage in circuits, and lastly we will see how impedance in RLC circuits, which translates as resistor, capacitor, and inductor circuits, are calculated using these trigonometric functions. I will be using slides of Alan Murray from Edinburgh University, and I present many thanks for that opportunity. In most fields of electrical engineering and in telecommunications, signals are usually represented in the form of waves. Not always, especially when in discrete time, they are not waves, but in most of the times and in the continuous domain, we use waves as the foundation of what we call signals. Waves can be defined using three of their main parameters, including amplitude, phase, and frequency. So if you know a wave's, or let's say a signal's amplitude, phase, and frequency, you can easily represent that specific waveform using the trigonometric functions we have already learned in the previous courses. These waves are eventually electrical signals, and these electrical signals are a result of alternating voltage and currents, as well as lead, lag, and phase shift. We have a mnemonic to remember how these electrical signals are associated with capacitive and inductive effects. It's called civil, and we will come to this later. Let's take a look at sinus and cosinus waveforms. We can represent a sinusoidal or cosinusoidal repeating signal as a short equation, as we have already seen in the previous course. Y equals to cosinus x is the most basic generic waveform. and as you can see, it has a fixed constant amplitude and a constant frequency on the x-axis. So amplitude is represented on the y-axis as our equation suggests, and frequency or the inverse of frequency, which is the time span or period of the signal, is followed on the x-axis. And y equals to cosinus 2x, which is the double angle, double of cosinus x. Sorry, it's double of the angle x, not cosinus x, of course. If we change the equation to this form, cosinus 2x, then we can observe the change on the charts. And as you can see in the chart, the change is not the amplitude of the signal, but it's the period of the signal. Now, in this form, we have a smaller period. So the signal repeats itself again, but this time with a shorter period. So it repeats itself faster. And this also translates as this signal has a higher frequency, and it's twice higher, 2 times higher frequency than the previous one. Similarly, if we change this angle 2x, which is the input of the cosinus function, to 4x, we will get y equals to cosinus 4x function, and this time we will have an even faster signal. These peaks and dips are much more frequent in this chart. This waveform this signal is in terms of frequency 4 times faster than the first one and 2 times faster than the second one. And there is absolutely no change in the amplitude of the signal, and there is no phase shift. The only thing that changed is the frequency. So whatever we put inside the cosinus function must be related to the frequency. Let's go a step forward, and instead of representing our waveform as y equals to cosinus x, let's represent it as y equals to y0 times cosinus x. Now, in this form, we have another parameter for the amplitude, which is y0. It doesn't have to be called y0, it could be also a for amplitude, but this is a common usage. As you see in the chart on the right side, the peaks from the x-axis has a magnitude, or let's say more properly the amplitude of y0, and this is easily observable from the chart. The distance between the x-axis and the highest point of these peaks, which are all the same, is y0 simply. Now in this form, we can both change the frequency of the signal and alter the amplitude of the signal. But what about the phase? Can we also change the phase using the same form? Well, yes, with a little bit of addition to this form, we can also change the phase of the signal and represent the signal with all its important parameters. And let's look at the second row, the 3 yellow equations, where it says y equals to y0 sinus x, or y equals to y0 cosinus x minus 90 degrees, or y equals to y0 cosinus x minus pi over 2. All of these 3 equations are exactly the same waveform. Why? Because in the first one, we changed cosinus x to sinus x, which caused a phase shift of 90 degrees, because the phase shift of cosinus and sinus functions with the given same angle is 90 degrees, or let's say pi over 2. These functions are very similar, and the main difference between them is their phase. It's not their amplitude. It's not their frequency. So the frequency is depending on the angle inside, and amplitude is outside of the function. The amplitude, which is y0 here, has nothing to do with the trigonometric function which comes after it. So amplitude is outside of the function. And x here is the angle, is the main frequency of the signal. And we can move this signal on the chart to left or right with a stated degree, and this will be our phase shift, and this will define the difference between the cosinus function and the sinus function in the circuits domain or signals domain. So here we are not dealing with the triangles themselves, but we use trigonometric functions to represent the signals. The theoretic fundamentals are still the same, but their application here is different, and as electrical engineers we care about that part a lot rather than the triangles. But if you talk with a construction engineer, probably they will think differently about these triangles. So if we take our if we take cosinus as our trigonometric function to represent that signal, we can subtract 90 degrees from the original angle, and we can get the sinus version of the same angle. And 90 degrees is equal to pi over 2. So this is why all these three equations are totally the same. And let's look at the last row. Here we also have three equations which all are the same again. Y equals to 2y0 sinus x, or y equals to 2y0 cosinus x minus 90 degrees, or y equals to 2y0 cosinus x minus pi over 2. So we already know very well that 90 degrees is pi over 2, so I will not be mentioning it again. But the important part here is we changed the amplitude part of the equation from y0 to 2 times y0. So we have doubled the amplitude, and it is observable in the chart if you look at the y-axis. So if you look at the vertical axis, we can see that these peaks of the signals are 2 times larger. Actually, if we consider the negative part, the difference becomes even bigger. But when we are measuring this amplitude, we always use the distance from x-axis to the peak on the y-axis. And this is how we represent the amplitude. We are not measuring the distance from peak to peak, but 0 to peak. And again, here, by changing the amplitude, we did not alter the frequency nor the phase of the signal. However, we are not limited to 90 degrees or its multiplications when it comes to phase shifts. We can shift the phase of a given signal by any degree or any radians. And this is usually represented with a Greek letter phi, or sometimes it's called phi. And in that case, the generalized form of our signal becomes y equals to y0 cosinus or sinus x plus phi. Here y0 is the amplitude parameter, x cosinus or sinus x represent the frequency. Actually, sinus and cosinus usually indicates the shape, the general overlook of the signal. X represents the frequency, and phi here is the phase shift. And it could be anything from 0 radians to 2 pi, or even larger, but after 2 pi it won't make any sense. because after 2 pi we will get 0 again, because cosinus and sinus functions have a period of 2 pi, so they will start repeating themselves, and it won't be possible to tell the difference between y0 cosinus x and y0 cosinus x plus 2 pi. Let's look down. Here we have y equals to y0 cosinus x plus 180 degrees, which is also pi. Here our phi is, the phase shift is 180 degrees. In this case, when you compare the third chart, the bottom chart with the top chart, you will see a major difference. Peaks became dips and dips became peaks. So it's exactly the mirror of the bottom chart is exactly the mirror of the top chart according to the x-axis. So it's symmetrical, but it's exactly the reversal of the top chart. And this is why y0 cosinus x plus pi equals to negative y0 cosinus x. This can be proven using the trigonometric functions identities, and it can also be proven using the signal representations, as you can see here. And the phase shift between one peak and one dip is 180 degrees, which is called pi. And if you think about that, this is very reasonable, because the period is 2 pi. So if you shift the signal a fixed length of 2 pi, then you will get the same signal. But if you shift it with 180 degrees, you will get the exact opposite of the signal. Positive parts will be negative and negative parts will be positive, while keeping the absolute value of the amplitude the same, because we have y0 as the amplitude, and when we shift this phase, or shift the phase of the signal, we will get the amplitude minus y0. But in the absolute value case, they will be the same. The distance from peaks to 0 and 0 to dips will be the same. And if we write the generalized form we have to write in the previous slide in a more generic way, especially for electrical circuits and electrical signals, we get V stands for voltage equals to V0 times sinus omega t plus phi. This tells us the sinusoidal variation of voltage over time. So the signals we were talking about in the previous slides are actually mapped to voltage in electrical circuits and electrical systems in general. So it doesn't have to be voltage all the times, but in many occasions, the amplitude here is the amplitude of the voltage. It can also be current or other parameters time to time, but we use voltage as the amplitude a lot of the times. So V is a function that changes over time and has other parameters than time, including frequency, phase shift, and amplitude, the base amplitude. And this base amplitude is represented with V0, and the signal V can have its maximum amplitude, which is V0, whenever sinus function returns 1. And this defines the peak points of our signal chart, as you can see on the right side. And we will get a temporal 0 as the changing voltage even though the V0 amplitude is kept constant, because sometimes sinus function will return 0. And these are the points where our signal just cuts the t-axis here, the horizontal axis. The unit of amplitude V0 is, of course, the volts. And the time located on the x-axis is measured by seconds. Frequency is represented with f, and it's usually cycles per seconds or points per seconds, or basically hertz. But we do not use time domain frequency here in our functions to represent the signals. Instead, for the sake of simplicity, we use angular frequencies, which is called omega, and exactly equal to 2 pi f. So converting time domain frequency to angular frequency is a pretty straightforward thing to do. We can replace omega with 2 pi f, or we can replace f with omega over 2 pi. So they are basically the same thing and pretty much convertible all the times. But for representing these electrical signals, we use angular frequency for the sake of simplicity and consistency. Phase is represented with Greek letter phi and measured in radians or degrees. If phi is 0, then the voltage function may become V0 sinus omega t only. So there is no phi if it is 0. And this means that there is no phase shift, but only frequency and amplitude. And this omega t part, the angular frequency times time part, has a unit of radians, because omega is represented as radians per second and t is, as you know, only seconds. So we will get radians when we multiply them. And omega t plus phi is basically radians plus radians. And this is why actually we use omega t for omega for simplicity. And this is also why y sinus omega t plus phi makes sense. Let's look at the components of an electrical circuit and see how the voltage and current behaves and how can we model them using trigonometric functions. Resistors are the most basic, simple units, simple stuff used in electrical circuits, and they are usually said to be trivial. However, it may not be the case always. Voltage measured on a resistor can be represented as V0 sinus omega t, considering that there is an alternating current source. So we are talking about AC circuits here, because when we are using DC circuits, the voltage ideally do not change over time, and there is a steady source of voltage or current, so we will get a constant voltage on the resistor, and we will measure a constant amount of current within the circuit. So it's not a problem, and this is the quite trivial part actually. But when we are talking about AC circuits with alternating current sources, then we have to formalize the voltage and current values over time. And VR, the voltage over the resistor, is found as V0, which is the maximum amplitude, times sinus omega t, where t is the changing time, the passing time, and omega is the angular frequency. IR similarly is depicted as I0, the maximum amplitude of the current measured in amperes, times sinus omega t. In resistors and resistor-only circuits, V and I, voltage and current, are in phase, so they follow the same phase and same form of functions. Even though their amplitude can be changed, of course, their units are also different, but the waveform, when we track or measure these values of I and V, we will get the same waveform. VR, of course, equals to Ri, the resistance value of the resistor, and the current value per to Ohm's law. It's the famous simple law of electronic circuits. Here R is the resistance value of the resistor, but in some sense it's the impedance of a resistor. And if we write this simple equation derived from the Ohm's law in terms of alternating current formulas, we will get V0 times sinus omega t equals to R times I0 times sinus omega t, again using the Ohm's law. And here we will get V0 equals to R times I0 again to prove the relation. As you can see, in both sides of the equation we have sinus as the main trigonometric function, and the same omega, same t, and there is no phi, no phase shift. So this is why we get the same waveform, even though the units and amplitudes are different for these two values. However, when it comes to capacitors, it's not that straightforward. It's quite easy to understand, but not that easy as resistors. The voltage in the circuit is originated from the voltage generating source. So basically the formula for the voltage must be the same. It is V0 times sinus omega t. It's still the same waveform with the given frequency and amplitude. But the current does not follow the same waveform. There is an observable and quite big phase shift. So it looks like when you apply the voltage source to the circuit and run the source and start the system, it looks like the current comes first to the capacitor, and then the voltage appears on the capacitor. So they are not coming on the device at the same time. So we will first observe the current, then the current starts to decrease, but the voltage starts to increase at the same time. And when the voltage hits its peak, current becomes non-existent, and it changed direction and reached the negative peak. At the same time, voltage becomes zero, so they are not in phase. And when we formulate voltage as V0 sinus omega t for the same circuit, the current becomes I0 cosinus omega t, which is equal to I0 sinus omega t plus 90 degrees, and this is the phase shift. To be more precise, Vc, the voltage on the capacitor, equals to Y0 times sinus omega t, and IC, the current gets through the capacitor, is I0 cosinus omega t, which is also said as I0 sinus omega t plus 90 degrees, or pi over 2. Here IC leads Vc by 90 degrees, and Yc can be formulated as Zc times IC from the Ohm's law, and here ZC is the impedance of the capacitor, and it replaces R from the IR, the most generic and simple form of the Ohm's law. So, and actually, to be more accurate, XC replaces R, which is the capacitor equivalent of the resistor impedance. Anyway, ZC here is the capacitor's impedance. In fact, ZC usually stands for the resultant compound impedance of all alike components, but here we only have VC, so the only capacitor, so XC can be seen equal to ZC. And V0 sinus omega t equals to some factor times I0 sinus omega t plus 90 degrees. And for satisfying the Ohm's law, V0 must be something times I0 using the amplitudes. And here we replace R with ZC, the impedance. And this resistance to impedance conversion, or this equivalency, makes dealing with capacitors not as trivial as resistors. A similar phenomenon also happens when we are working with inductors. VL, the inductance value of an inductor in a circuit like the picture on the right side, can be represented with VL equals to V0 sinus omega t, just because of the same source of alternating voltage. Here, the current comes after, unlike the capacitor. IL, the current passes through the inductor, equals to I0 times sinus omega t minus 90 degrees. Here the phase shift is not plus 90 degrees but minus 90 degrees. And this translates as IL lags VL by 90 degrees. And from the Ohm's law, we get VL equals to ZL times IL, and here ZL replaces R. And in other terms, XL replaces R. But if we have more than one devices, then we have to calculate ZL from XL. However, here we only have one inductor device, so XL must be equal to ZL, which is the impedance, inductor's impedance, and it is the inductor's equivalent of a resistor's resistance. And for the same reason as capacitor, we get V0 sinus omega t equals to some factor times I0 sinus omega t minus 90. And this is where ZL takes place. And do not forget the phase shift here is minus 90 degrees. And from the bottom two charts on the right side, you can see that we first observe the voltage on the inductor device, but the current comes after. So when there is voltage, there is no current. When there is the peak current, there is no voltage. So there is a clear lag, easily observable from the charts. And let's go over what we have found. VR, voltage of a resistor, equals to R times IR, resistance of that resistor times current of that resistance. Here R is clearly a resistance. For a capacitor, VC is ZC times IC, and ZC is officially an impedance, not resistance, because resistance is unique to resistors. It cannot exist as it is in inductors or capacitors. But there is an equivalence of resistance in these devices called impedance. For capacitors IC, the current leads VC by 90 degrees, and this makes VC equals to VC0 times sinus omega t, and makes IC equals to IC0 times sinus omega t plus 90 degrees inside the sinus. ZC describes the magnitude relationship between V and I, and ZC must also describe the 90 degrees phase shift in some magical way. However, if we only consider the amplitudes, we will get VC0 equals to XC times IC0. And in this relation, we call XC is the capacitor's reactance. And XC exactly describes the relationship between the magnitudes of V, the voltage, and I, the current. But XC does not describe the phase shift, which is represented with phi. This must be described by the sinus omega t part of the equation as like sinus omega t plus phi. So the XC value of a capacitor or ZC value of a capacitor or a group of capacitors cannot describe the phase shift phi. It must be embedded into the sinus function and make sinus omega t to sinus omega t plus phi, where phi represents the phase shift in terms of angles. And this is where the mnemonic civil makes sense. Here, let's look at the first three letters of civil, which are CIV. We can say that in a capacitor, current I leads V voltage. So in a capacitor, current I leads voltage by 90 degrees. It's called CIV. For capacitor, current leads voltage. First current comes, then voltage appears. And the difference is 90 degrees, plus 90 degrees. And let's look at the last three words of the same word, last three letters of the same word. And we get voltage leads current I by 90 degrees in an inductor L. So voltage leads current I by 90 degrees in an inductor L, VIL. For inductors, voltage comes first, then current comes after. This is the case for inductor. Let's dive deep into more details and look at the capacitor reactance XC. And do not forget the angular frequency omega is equal to 2 pi f, where f is the regular frequency. A capacitor blocks DC signals where f equals to 0. So when frequency is 0, then we get a DC signal with no alternation and no signal forms. And if f equals to 0 in a DC signal, then omega would be also 0, because omega is defined as 2pf, and whenever f is 0, omega will be also 0 because it has f as a factor inside. This is why actually capacitors block DC currents. On the other hand, a capacitor passes AC signals where f is greater than 0, which will make omega greater than 0 because f is inside omega, and 2 pi will not change the value of f and will not affect this amplitude. And per the Ohm's law for amplitudes, V0 is XC times I0, so reactance of that capacitor times I0. And it turns out that V0 is equal to 1 over omega C times I0 for a capacitor only. And here we can also say it blocks DC signals and passes AC signals. And from this relation we get XC equals to 1 over omega C. And for DC current, F will be 0 and omega will be 0, and XC would be infinite, so it will be huge or really infinite. And as XC is a sort of equivalent of a resistance, as in resistors, but in a different way. An infinite resistance will block the signals or currents. So this makes really sense. For AC, F will be greater than 0, and omega will also be greater than 0. So XC will be smaller than infinite, and for a reasonable XC value, we will get our signal pass from that sort of resistance. And if the current equals to I0 sinus omega t, then the voltage would be 1 over omega C, where C is the capacitance, times I0 sinus omega t minus 90 degrees, and here minus 90 degrees will be the phase shift, the lag. Similarly, we can also take a look at the inductor reactance XL. An inductor, as opposed to the capacitor, passes DC signals where F equals to 0 and omega also equals to 0. But contrarily, it blocks AC signals where F is greater than 0, and by the way, omega is greater than 0 because it's 2pF. And Ohm's law for amplitude similarly indicates that VL0 equals to XL times IL0. So it turns out that V0 equals to omega L times I0 for an inductor, which blocks AC current and passes DC current. So XL, the reactance XL would be omega L only. And for DC, F would be 0, omega would be 0, and XC would be 0. So we will get little to no resistance at all, and the signal will pass. For AC, frequency would be non-zero as well as omega, and XC would be greater than 0, and it will start to block our signals or currents at a degree. And if I is defined as I0 sinus omega t, then V must be omega L times I0 sinus omega t plus 90 degrees, and here plus 90 degrees part is the phase lead. Here there are some example questions for you to answer. We ask ZR for a 1 kilo ohm resistor at 10 Hz, 10 kHz, and 10 MHz, and the same for a capacitor, ZC for a 10 microfarad capacitor at 10 Hz, 10 kHz, 10 MHz, and similarly we ask ZL value for a 0.1 millihenry inductor for all these 3 frequencies. I suggest you to stop the video here and find your answers, and for comparison or for result checking you can use an online calculator found on Google, and you can try other combinations as well. There are plenty of them online. So let's sum up what we have so far. If I, the current in the circuit, equals to I0 times sinus omega t, VR for the resistor equals to R, the resistance, times I0 sinus omega t, and VC must be 1 over omega c times I0 sinus omega t minus 9t, representing the phase shift. And VL, voltage of an inductor, must be omega L times I0 times sinus omega t plus 90 degrees. And all obey Ohm's laws with different constants between V and I. So the relation between V and I depends on R or XC or XL, which are R, 1 over omega C, and omega L. In capacitors, I, the current, leads voltage VC by 90 degrees, and in inductors, voltage VL leads the current I by 90 degrees. These are the essential parts, the essential topics regarding how we use trigonometry in electrical engineering and its subtopics. There are, of course, many more application fields and many more advanced topics about that, and we may consider continuing our courses about these applications if we get demand from students and professors. Thanks for watching and listening.